Hello and welcome back to FPV Reviews. Today we'll be examining the flight dynamics, aerodynamics, and structural considerations of twins and multi-engine aircraft. First, there's the obvious advantage of having an extra engine in the case of a failure. Of course, with a twin, you're twice as likely to have an engine failure in the first place, assuming you're operating both engines for the entire flight. Now, the vast majority of multi-engine tractor designs have their engines mounted on the wings, so we'll discuss them first. Now, the elephant in the room here is the offset thrust in the event of an engine failure. With reciprocating engines, it's not a matter of if, but when it will happen. In the case of turboprops and jet engines, it's much less likely. However, today's multi-engine turboprops and jets are usually very large in size, and many lives are at risk if things go wrong. So it's worth consideration. Although it's one thing to design unmanned vehicles with a certain acceptable level of attrition, the same cynicism is not acceptable for manned aircraft. For them, it's absolutely necessary to carefully consider what happens when an engine fails and design the aircraft to have the best possible characteristics when such an event occurs. Of course, designing the propulsion system for maximum reliability is the best possible solution so as to prevent the failure in the first place, and the use of electric motors is probably as close as we can come to achieving that goal. When an engine does fail, what's obvious is that the thrust is now asymmetrical, but there are other effects that come into play as well, the degree and specifics of which are determined by the decisions made during the design process, such as how far from the center line the engines are located, and which direction they rotate. For example, many twin-engine aircraft use engines which rotate in the same direction, in which case there will be a critical engine, one that has more severe and adverse effect to the overall handling if its propeller stops producing thrust. Ideally, the propellers would turn in different directions, enabling the pilot to focus on coping with the situation and simply identifying which engine to shut down, rather than having to worry if it's the critical engine or not. It's important to shut down the correct engine in this situation, reduce its drag as much as possible by stopping the prop from turning and feathering the prop, as the effect of the asymmetrical thrust from the good engine will yaw the aircraft in the same direction as the drag from a spinning prop that has not been feathered. This also serves the purpose of reducing the overall drag of the airframe to get the most performance possible with an engine out. Flying with asymmetrical thrust also means the aircraft will then be flying sideways to some extent, creating more than the usual form drag from the fuselage, so there will be that additional benefit to getting the prop stopped and feathered as well. Most twin-engine aircraft with wing-mounted engines have a minimum control airspeed, so if the pilot has kept the aircraft above that speed and lowered the nose appropriately as soon as the engine failure occurs, he will have enough control surface authority to maintain good overall handling characteristics. Let's examine the effect of torque, P-factor, gyroscopic precession, and slipstream effect on a twin-engine aircraft that has just lost an engine. If the props turn the same way, one engine's torque will be trying to counteract the asymmetrical thrust that is present, helping to make this bad situation less severe. If the opposite engine, also known as the critical engine, fails, the aircraft would tend to roll in the same direction that the asymmetrical thrust is trying to yaw it, making the overall situation even worse. Coincidentally, P-factor, gyroscopic precession, and slipstream effect will also have a turning effect on the aircraft's yaw axis in the same direction as the torque. The torque will vary with engine RPM, airspeed, and propeller pitch, as will P-effect, gyroscopic precession, and slipstream effect, except that they will also be more accentuated with an increasing angle of attack of the wing. These factors all conspire to turn the aircraft uncontrollably in the same direction when the critical engine is lost below a certain airspeed. That's why airspeed must be kept above VMC, or the minimum control airspeed, to keep sufficient air moving over the control surfaces on any aircraft where the props turn in the same direction. If the props counter-rotate in the proper direction, that is, turning inboard at the top of their arcs, then torque, P-effect, and slipstream effect will all counteract the offset thrust from the engine left running, helping to restore some balance to the aircraft rather than making things worse. Planes with counter-rotating props which rotate in the proper direction will therefore be able to have a lower minimum control airspeed than if their props rotated in the same direction, and therefore inherently safer than planes which do not. So, aircraft designers would all make sure the props counter-rotate, wouldn't they? Well, sadly, no. In order to standardize engines and propellers, it's extremely common to find twins which have the same direction of rotation for both engines. It would cost the same to produce the engines and props themselves in two different varieties. However, the cost of tooling and spare parts to stock would be higher. Although most parts in an internal combustion engine do not care which way the engine rotates, some parts are directional, such as starter motors, camshafts, some timing parts, gearboxes, and some types of oil seals, to name a few. The firing order will also be different, along with the propellers and sometimes their associated hardware. It can also be confusing to the people assembling the engines and working on them, as some parts must be installed in a different orientation in the engine, such as pistons. A small mix-up could cause a major failure. Some manufacturers have been known to cut corners by reversing gearbox only on one engine to standardize engine rotation while still allowing the props to counter-rotate. This is not a great solution, however, as there is an inherent loss of an efficiency in adding a gear to one of the motors that is not matched on the other side. Even if it were perfectly reliable, it would be mismatched just slightly. Without an easy solution, many manufacturers would rather save the money and effort rather than do the right thing in this regard, and many pilots accept this as perfectly normal. With electric motors used for propulsion on twins, however, there is no excuse, as they have no fixed direction of rotation, and it's just a matter of making reverse-pitched propellers for them to achieve counter-rotation. Simply changing a couple of wires will make sensorless brushless motors spin the opposite direction, and brushed motors can do the same with a change in polarity. In a multi-engine configuration, whether it be a twin or a four-engine aircraft, which are the most common types, the designer also gets to decide whether to place the tail and its control surfaces in the prop wash or accelerated air or not, and if so, to what degree. The choice is mostly dependent on whether the aircraft will be used in situations where control must be maintained at very low airspeeds, usually to land in very short distances on unimproved runways. If that is not necessary, then keeping the tail clear from the accelerated air is usually the best approach, as it's easier to predict how the aircraft will behave at a given airspeed and control surface deflection. This clean characteristic is useful for flight training, commercial flying, and also permits the autopilot of an unmanned aircraft to be tuned properly, since it is not aware of the accelerated air over some of the control surfaces some of the time. The tuning usually ends up being done with the aircraft in cruise flight with a moderate amount of accelerated air over the surfaces, and the control response from the autopilot is only proper then. In a glide, such as landing approach with the props at a low RPM, not enough controlled deflection will be used by the autopilot, and not quickly enough. During a climb, such as when taking off at full RPM, the autopilot will then tend to overcorrect, resulting in an overly energetic control response. This may work, however, but it is far from ideal. Keeping the control surfaces clear of the prop wash completely solves this problem, and it is easier for student pilots to master as well. With wing-mounted engines, it's also practically inevitable that some accelerated air is blown over the wing surface behind each engine. This causes an increase in induced drag, although it contributes to the lift of that part of the wing, so does not significantly reduce the efficiency of the overall aircraft. Most planes need more distance to take off than they do to land, and by contributing significantly to the lift during takeoff when RPM is the highest, the plane with wing-mounted engines gets off the ground in a shorter distance, more closely matching the landing distance. For some situations, it can mean the difference between being able to take off again from a given location where a landing was made, rather than having to disassemble the aircraft to truck it out. It does mean that twins are especially more susceptible to tip stall of the wing, as there is more lift toward the center of the wing, where the engine nacelles are located, than the outer sections with power on. This must be taken into account by the designer in the selection of the wing plan form, the degree of the wing's washout or twist in the outer wing section, and any devices used to prevent tip stalls. The twin configuration, and especially the four-engine configuration, do lend themselves from a structural standpoint to the use of a high aspect ratio wing due to their weight distribution. These long wings help provide a damping effect in roll during a tip stall, and also with power on stalls, limiting the maximum bank angle during the stall, and usually more than making up for their increased propensity to tip stall. High aspect ratio wings are more efficient in terms of distance and endurance optimization, also allowing heavier payloads to be carried than would otherwise be possible. An aircraft with a large wingspan is less susceptible to upsets on the roll axis from turbulent air and provides the pilot more time to make corrections, reducing their workload or the duty cycle for the autopilot and actuators on unmanned vehicles. The ailerons do not necessarily have to be any larger, as they are now located further from the center line of the aircraft. There's nothing that says that a twin has to have such a high aspect ratio wing, however, that it cannot be used as a fighter. And there are many successful examples of them being used for multi-role fighter bombers, interceptors, and even for low-level fast attack aircraft during the peak of prop-driven planes, the World War II time period. With the clean aerodynamics they offer combined with the use of counter-rotating props, nothing handles better than a twin at high speeds while still retaining agility. There's one airplane that breaks the mold of counter-rotating twins, however, the P-38 Lightning by renowned Lockheed designer Kelly Johnson. Most examples of this fork-tailed devil, as its enemies in the Pacific called it, rotate the propellers the wrong way, outwards at the top. Many of the early prototypes rotated in the normal safe direction. However, it was found during testing that the aircraft itself was more stable at high speeds with the props rotating the opposite direction, outwards at the top, although it actually hurt its single-engine performance at low speeds. This is partially compensated for by the fact that its control surfaces are directly in the prop wash, so if one engine is still running and power kept on, the control authority will be better than with most twins. This feature of its layout also helped it to maneuver better as a fighter at medium to low speeds in a turning fight. Being a twin, it was also possible to use differential thrust at low speeds to gain an advantage in maneuverability. High-speed stability was supremely important for the P-38, however, as its primary function was as an interceptor and a gun platform. Rock-solid stability at speed made for better aim with its 4 50 caliber guns and 20 mm autocannon, which were placed in the center nose fairing. This was also a prime location, as it allowed more guns than usual, along with concentrated alignment of the guns to group the shots tighter than was possible in single-engine fighters, where the angle of the gun's barrels on the wings had to be offset slightly toward each other, resulting in a good cross-grouping of the shots at only one range. In the case of the P-38, safety was quite dependent on being able to shoot down other aircraft before they shot you. And during wartime, the relatively small trade-off of engine-out handling was one worth taking for the designers and the pilots who flew it. Even with its unconventional prop rotation, many P-38s made it back from their missions just fine on their one remaining engine. Interestingly, the same backwards rotation was tried on the F82 Twin Mustang, a North American aircraft made by joining two stretched P-51 fuselages with an all-new wing design. However, it caused problems as the air trapped between the two slab-type fuselages created severe drag for the center wing section with its interaction. That just goes to show how even small considerations, such as the direction of prop rotation, should always be matched to the rest of the airframe, especially in an unusual configuration such as the F-82. After a month of pulling their hair out, wearing out their slide rules, interrogating the test pilot, and breaking their pencils, the now bald engineers at North American found the solution: to simply swap the engines from right to left, and most subsequent production models were made with the props turning inward at the top. In the end, the F-82 Twin Mustang ended up with much better range, cruise speed, top speed, and payload potential than the original P-51 Mustang, although it used the same fuselages and engines. This performance advantage is typical of the twin configuration and is the prime reason for their widespread implementation in military and commercial applications. Full-scale pilots wanting to get their multi-engine rating will find that flying a twin is easy when both engines are functioning properly, and you get to enjoy the benefits of the increased performance that twins offer. The pilot workload and complexity of procedures increase greatly, however, when a failure happens, so it's important to get it right. The training will start on the ground, not only to help the pilot understand the flight dynamics which we so briefly discussed, but also how density, altitude, gross weight, and crosswinds will affect the engine-out performance of the aircraft. Familiarization with the performance charts for the specific type will help to understand the particulars of performance as it relates to safety. Most pilots do their initial training in a light twin, such as a Piper Seminole, as these aircraft have benign and forgiving flight characteristics, allowing the pilot to focus on the training without having to wear their brown pants for their first flights in a twin. Some pilots go far beyond training for safety in twins, however, and learn to fly them in a performance role. Bob Hoover was one of such pilots. Coming from a career as an Army Air Force fighter pilot and test pilot, he became widely recognized as a superb multi-engine flight instructor, airshow pilot, and aviation record setter. Famous for his engine-out routine and his Aero Commander Shrike, in which, among other maneuvers, he could successfully pour a cup of tea while performing a 1G roll. His precision flying, often with one or both engines shut down, opened the eyes of many to what is possible with an aircraft originally developed as a light business twin. The dynamics of engine failure in aircraft with 4 and 6 engines are similar to the twin, as we discussed, except that in the case of a 4-engine aircraft, loss of thrust from only one engine only represents a 25% loss of total thrust instead of a 50% loss of total thrust in the twin. Most 4-engine aircraft can even afford to lose more than one engine, but preferably not on the same side. The severity of an engine-out situation will now depend more on if it was an inboard or outboard engine that failed rather than the direction of rotation of the individual engine. If it was an outboard engine, the severity of the thrust asymmetry is comparable to a standard engine failure in a twin, except that with a smaller relative prop diameter, the offset due to P factor causing unwanted further yaw, along with the rolling effect of torque moment and any slipstream effect due to stabilizers within the prop wash area, will be slightly less than with a twin. If an inboard engine fails, then the situation is far less severe, as the failed engine is much closer to the center line of the aircraft. The failure still matters, but not nearly as much, so it makes more sense for four-engine aircraft to go ahead and standardize their parts and let the engines all rotate in the same direction. The same factors apply for six-engine aircraft. Their overall odds are just that much better in almost every way. Very few aircraft have been made with six or more engines, presumably because after four, the safety advantages are just marginal, and the likelihood of having an engine failure in the first place is much greater. There are some notable exceptions, however. During the golden age of aviation, having many engines would result in so many failures you would be practically planning to replace engines very often, would often have to keep one at the destination that the aircraft was likely to visit. For more modern aircraft, this would mean more downtime and thus a loss of revenue for the airline, as well as inconvenience to the passengers. With advances in high bypass ratio turbofan efficiency, designers of the latest generation passenger jetliners have gone back to twin-engine layouts rather than the four-engine configurations of previous generations still in service, such as the Boeing 747 and the Airbus A380. Less engines means less chance of failure. We usually think of asymmetrical thrust as a fault. However, it is often used to help maneuver aircraft on the ground while taxiing. It occasionally comes in very handy as a way to control large aircraft which have lost all their normal and redundant hydraulic flight control systems in flight as well, and would otherwise be doomed. Several flight crews of large commercial airliners have managed to land successfully in this condition. After seeing the potential, designers created a system whereby the primary flight controls can manage the offset thrust of the engines using a computer interface, giving the pilot a much better chance of getting the aircraft on the ground safe, even in the event of a catastrophic failure of this kind with the control surfaces. Pilots who have tested the system report it to feel almost normal, just slightly sluggish. Truly an amazing technological breakthrough in aviation safety. There are also structural benefits to having multiple engines, as the weight of the propulsion system and related components is now spread out over the wing spar rather than concentrated in the center, enabling the structure to be lighter and stronger. Fuel is typically stored in the wings as well, so the fuel is closer to the engines. On high-wing twin commuter turboprops, the engine nacelles also provide a convenient place into which the landing gear can be retracted. This is usually further out on the wing as it would otherwise have been practical to place the gear, so the aircraft can end up with a wider stance for the mains, improving its performance during a landing with a high crosswind component. This is a major safety factor, and that's one reason why this configuration is widely used today for regional air transport. The basic configuration is also seeing increased use for long-endurance UAVs as it provides a large volume fuselage well isolated from engine or motor vibration, along with a clear view of the ground and sky for the payloads and sensors. The twin tractor configuration is even becoming dominant in the FPV hobby market and with inexpensive autonomous mapping UAVs, as demonstrated by all the newest hobby products. Although many of these are borrowing the general idea from other designs, they may still represent an emerging trend, even though some of the people promoting the aircraft don't even know which way the props are supposed to turn. Multi-engine aircraft also lend themselves to extreme short takeoff or landing performance, as the accelerated air blowing over the wing gives extra lift. If slotted flaps are used, it's even greater. If multiple engines are placed evenly along the wing surface, the coefficient of lift can be much higher for a given airspeed than if the wing was simply lifting by itself. The versatility of the de Havilland family of aircraft, such as the Twin Otter and the Caribou, are well known in this regard, as well as the C-130 and other similar types. Now, we all love how a tri-motor looks, but in a practical sense, there are some unique advantages. If a tri-motor loses an engine, there's a 1 in 3 chance that the failure will be in the center engine, and no significant change in thrust offset will occur. Only about 1/3 of the total thrust will be lost, and it's very likely that the passengers will still be able to reach their destination safely, perhaps even on time. With the center engine not running, they may not even experience much hearing loss after their trip. If one of the outboard engines fail, the offset thrust and drag issues will be less severe than with a twin, and overall thrust will be better too. No wonder pilots, passengers, and the airlines loved tri-motors back in the days of early aviation when engines were not that reliable. In fact, many tri-jets are still in service today as modern airliners. Just don't do it like this, okay? I thought we got over that stage. Well, not all twin-engine aircraft are configured in the usual way, as there are inline variants which use an engine mounted as a tractor and another as a pusher. These have the distinct advantage of having both engines directly on the fuselage centerline. In the case of the inline twin, an engine failure need not be an emergency, or need not necessarily require diverting from the intended destination. In most regions, even, the multi-engine rating for inline twins is also much easier to obtain for the pilot. Many forward-thinking aircraft designers have used this configuration to achieve spectacular performance figures while retaining some of the best safety statistics in the industry. Others have made more conventional aircraft that suffer from rear engine overheating on the ground and being underpowered, however. It's common for inline twins to have different pitched propellers on the front and back engines, as the air entering the prop arc on the front engine is slower than the already accelerated air entering the rear prop arc. There is a small amount of efficiency loss from having the air recompressed by the rear prop, as it raises the effective disk loading on the combined propellers. This effect is lessened if the props are further apart, and the air has a chance to decompress before reaching the rear prop. Having both engines in line also serves to reduce drag, and the fuselage can fit in between. This unique performance advantage allowed aircraft such as the Dornier 335 to achieve jet-like speeds of up to 475 miles per hour in level flight, making it Germany's fastest piston-powered aircraft of World War II. Several design challenges were encountered for this configuration, including how to allow the pilot to bail out without getting chopped to pieces by the rear prop and crucifix-style tail. Also, how to reduce the likelihood of a rear prop strike during rotation. The bailout issue was solved by using explosive bolts to jettison the canopy, rear propeller, and dorsal fin before the pilot could bail out using an injection seat, which had just been invented in its modern form a few years earlier in the war. There were relatively few inline twins during this time period, and although they were highly successful, the age of prop-driven interceptor aircraft was giving way to jets. It would not be until much later that commercial interest would bring back the relative popularity of the inline twin. with so much performance potential, it makes one wonder if strange-looking aircraft are often sidelined by decision makers in favor of more conventional designs, despite their greater potential. Speaking of potential, some inline twin-engine aircraft have two different types of propulsion systems. One optimized for maximum thrust to assist with takeoff, climb, and to be used in case of a failure of the second, which is optimized for efficiency. The efficiency optimization favors either cruise or loiter, depending on the mission for which the aircraft was designed. For instance, in the last video, we briefly discussed the power system on Voyager, the first plane to fly around the world non-stop and non-refueled. The aft engine, without as much as a starter motor in an attempt to save weight, was a 110 horsepower liquid-cooled Continental, designed to run for up to 300 hours straight for the trip around the world. It started life as a Model 0200 and was modified specifically for the Voyager mission. The front engine was a conventional 130 horsepower air-cooled aircraft engine with an electric starter motor. It was meant to be used for takeoff and for the portion of the flight when the aircraft was the heaviest. It was shut down once some fuel had been burned off, and Voyager was capable of flying without it. It was intended to be restarted in case of an engine failure of the rear engine to give the plane the capability to extend its glide or divert to an airport. Flown by Dick Rutan and Jana Yeager, Voyager set two major world records. One for distance after flying around the world near the equator, reaching 26,366 statute miles, and one for the longest takeoff run in the history of aviation, while literally dragging its wingtips on the ground, using about 14,200 feet, or 95% of the available runway at Edwards Air Force Base in California, the longest runway in the world. If Jana had not cut her hair before the flight, it would probably never have lifted off. Another of Burt Rutan's designs was a twin fuselage aircraft called Boomerang, named for its forward-swept wing, that also used two different sized engines, this time for a practical purpose. Having the two fuselages and staggering them meant that the twin engines could be placed closer together to the overall center line than normally possible. This means less asymmetrical thrust for either of them if the other were to have a failure, although both engines in this case were intended to run constantly. The right engine was 210 horsepower, whereas the left engine was 200 horsepower. What this means is that even at altitude, and when on a trip across the United States, an engine failure only meant a 50% chance of forcing the pilot to divert, and consequently a 50% chance of being able to continue the climb over the Rocky Mountains with the higher horsepower engine and on to the destination even at full gross weight, whereas most twins would absolutely have to divert if either engine failed. Congratulations to Burt for finding an innovative solution to a problem which never actually happened, while using a configuration which gave more normal people headaches to look at. There are also twins which, although they may not have different engine sizes, do manage to place them closer than normal to the center line, such as the PBY Catalina flying boat. With the fuselage below the engines, instead of in between them, each engine's thrust line is close to the center line, therefore decreasing the severity of the asymmetrical thrust when one quits. Even the little Cree ultralight, in its two-stroke gas or electric versions, manages twin-engine reliability with limited asymmetrical thrust when an engine is lost. One way to gain the redundancy that multiple engines can provide without any significant asymmetrical thrust if one fails, and without the high failure rate of all those engines, is to use mini electric motors for the actual propulsion. This concept is called distributed electric propulsion. and can come in several different forms, including conventional propellers, prop fans, and ducted fans. The power for the electric motors can come from a variety of sources, such as a reciprocating or turbine generator, propane or hydrogen fuel cells, a power takeoff from a centrally located turbofan, hybrid fuel, electric power, solar power, and of course, pure battery power. Any aircraft powered by 3 or more electric motors in a span-wise configuration which blows air over a lifting surface is technically using distributed electric propulsion. More about how this improves performance and efficiency in a future video. So, in summary, multi-engine aircraft have great performance potential. Inline twins have great potential where reducing drag is a major factor without having to worry about handling if an engine quits. Twins with span-wise engine mounting solve virtually all of the problems associated with single-engine aircraft, and provided that the props counter-rotate in the proper direction, they are quite safe with improved distance and endurance potential. Tri-motors provide even more reliability than a twin, with even less consequence if an engine fails. And planes with 4 engines or more provide the ultimate in reliability, comfort, and utility. So please let us know your thoughts in the comment section down below. Smash that like button, hit the bell icon to get notifications when we upload a new video, and if you'd like to contribute as little as $1 to help us making these videos, click the link in the description below to easily do that. Also check out our website's secret page with lots of hidden data. We'll be putting a one-time link in the description to that of this video, because if you made it all the way through this video, you're just that kind of person. There's also a lot of additional information in there about our own unique twin electric aircraft designs that you'll surely find interesting. Thanks for your support of this channel, and until next time, have a good one.